Working with at the time 2 graduate students at Princeton, Ankit and Rafael, who are here, on some algebraic complexity question actually having to do with non-commutative circuits. Things started with Amir Yodayev and Pavel Hubesh, who are also here. And we somehow ended up needing to understand this invariant theory, a lot about invariant theory, and these 3-4 years have been very enlightening for us and productive for us. And we also collaborated with a bunch of other people. Some of them know much more about this field and algebraic geometry and presentation theory than us. We learn a lot from them. And what I want to share with you today is I'm not going to talk about our work much. I'll talk mainly about invariant theory, but the perspective that I got into it through this work, and I want to really sort of convey to you how closely related this field is to us. And you'll see lots of examples. There'll be lots of examples in the talk. You don't have to, follow every example, the details of every example, but you'll see lots of familiar objects, notions, results that will ring with you, I hope. In a way that will somehow relate or see the relationship between these two fields. And in fact, there's a lot that happens in invariant theory that is so close to our instincts, I think, that there's a lot to learn from them, and there's also a lot to contribute to them, collaborate with them, and I hope this will become clear in this talk. I want to start with a bit of, but actually I think I'm a bit anemic, and I think I'll just take a chair just in case I'll need to sit. I just feel that it's maybe needed. So I'm sorry about that. It's happened to me already once before in the last few months. All right, great. So, yeah, I'll sit if I'll take it here, just because I'll put this stand here. So I want to start with a bit of some prehistory. It's a personal prehistory, but somehow something that helped me get into these questions and these connections. About 20 years ago, I was working with Nati Lina and Alex Samolnitsky on some problem that I'll show you, and we developed this really cool algorithm. And it turns out this cool algorithm was discovered numerous times before in various contexts. It's very important, but this will not be the focus. And I want to tell you about this algorithm, and maybe that's the only algorithm you'll see. So what's the problem? It's a matrix scaling problem. So you have a non-negative matrix, and like this one, is the adjacency matrix of some graph, happens to be. And you want to make this matrix doubly stochastic. So you want to make it row sums 1 and column sums 1. Okay? And what are you allowed to do? Well, you are allowed to multiply rows and columns by constants. That's what you're allowed to do. And it's not clear how to do it because they interfere, columns and rows, but there's a very natural thing. This cool algorithm is really something that comes naturally. It's sort of greedy and maybe naive and stupid if you think about it, but you shouldn't think about it. You should just try it. Say, okay, let me fix the rows so they are stochastic. That's easy, right? Okay, right? You just normalize the rows. But the columns are not, so then you say, okay, let's do the columns. Now the columns are fine, but the rows are not fine, so then you fix the rows again, then you fix the columns again, you fix the rows again, see what happens. And it turns out that this is what happens in the limit. It converges, and it converges to this matrix, which is doubly stochastic. And it turns out to be a theorem that this converges if and only if the permanent of the matrix was positive, namely if the graph, the associated graph, had a perfect matching. And in fact, if it converges, it always converges fast in polynomial time. So this means that this algorithm is probably one, if you've never seen it before, is a very different algorithm for perfect matching that is not normally taught in classes, but it's maybe the simplest to program. It's just 2 lines. So that's one fact about this. And the other fact in this paper, Alex, we had an analysis for it that was somewhat different than previous analysis, and at the time we had no idea, but now we understand it much better, and the right way to view that analysis and to understand this algorithm is through invariant theory, and we'll understand it better towards the end. So the outline of the talk is, I want to tell you about what invariant theory studies, or some of what invariant theory studies, their motivation, their questions, their results, their notions, their structure in there that they developed. And it has two parts which interact really well, an algebraic part and a geometric part, or analytic part. And they interact very well, and we'll see it when we get to this optimization and duality view. Towards the end, I'll explain about this magical moment polytopes. And I'll talk just a very little about algorithms, and then there'll be more talks in the workshop by Ankit and by Raphael that you'll hear more about these algorithms and some of the other work that's related to this project, I would say, connections between complexity and optimization with invariant theory. So that's the plan. And stop me with questions. So what does invariant theory do? It studies symmetries, group actions, orbits, invariants, and it occurs all over. It has applications all over in mathematics, in physics, and computer science. So here are some examples. So you have to have a group, and it has to act on some set of objects. For example, the symmetric group here acts on the labels, on the names of the vertices in graphs. That's a very simple action we know, very simple to describe. Here, the group is just the real line, just time acting on the set of configurations of a billiard table. Right? Once you hit the ball, then it evolves over time, and these are this is the action. That's a nice one. Here you act on just planar configurations by scissors and movement of pieces around. It's another group. And in each of these, so there's motion, there's action, there's dynamics, right? The group is, you can apply various group operations. Things are moving, but some things don't change. These are invariants. That's the word invariant theory. Then where the invariant comes in. For example, in the last example, the area doesn't change as you cut and move things around, non-overlapping, right? In the billiard, we know it's a physics example. Many of these processes preserve things like energy, momentum, and so on. So these things don't change. In the case of this graph isomorphism, we don't really understand the invariants. They're there, but we don't understand them. And computer science, I didn't, it's physics and math here, but we know this dynamics, just computer programs. They evolve the values of variables, and often we analyze them with invariants, right? There are invariants that we keep track of, and that, of course, will be very relevant to the analysis of algorithms that we'll talk about. Okay, so that's a very, very high-level view. We will look throughout the talk at very particular types of actions. The groups we will look at are linear groups, and I wrote here examples of the linear groups we will talk about, so they'll be on the board. Maybe but anyway, you know them all, so you don't have to think about others. The general linear groups of all non-singular matrices, and its subgroups, the special linear group, are all determinant, just those with determinant 1. These are non-abelian groups. Here are the abelian groups, which are the same, only that you allow only diagonal matrices. So the torus is just non-zero values on the diagonal, and the special torus is non-zero values on the diagonal with determinant of 1. And we'll just look at, you can think of just these groups. All the examples will come from these groups or products of such groups. These are the only things you'll see, even though the theory I'll talk about is much more general. It applies to all so-called reductive groups, and it happens where this mapping I'll tell you about is rational. So let me talk about what I mean by this linear action here. So the linear action is just that you want to think of your group, whatever it is, as a group of matrices. And you'll see examples you are really familiar with, but in general, the way to think about group as matrices is to every element G in the group you assign a matrix which acts on this vector space. So the action is always on what the objects you move is just vectors in a vector space. Vector space over a field, which for us throughout the talk will be the complex numbers. Okay. And so what does it mean that every element is represented by a matrix? This satisfies what you want it to satisfy, that, you know, these matrices, when you multiply them, compose like the group elements. You have an identity and you have an inverse and so on. Here are examples you are familiar with. Let's say G is a symmetric group. It acts on vectors Sn. It acts on vectors of length n by permuting the coordinates. So this M sigma for permutation sigma is just a permutation matrix. Here's another. G is a general linear group acting on a vector space of matrices now by conjugation. That's a linear action, right? It's a linear action on the matrix X. And I want to stress here that here the number of coordinates, X is n squared. The matrix is n by n, but there are n squared coordinates that are moved about. So you can or sometimes think about when this is, you represent it like this. X is a long vector of n squared coordinates, but it's concisely represented this way. Okay, so these are examples of linear actions. And here are the objects, the main objects that are being studied in this type of actions. So the first thing to notice when you act on a vector space and you have some coordinates for this vector space, you can think of them as variables. And so you are acting on the variables, and thereby you are also acting on polynomials in these variables. Okay, so the first object and very important object is invariant polynomials. Invariant polynomials are exactly polynomials in these variables which remain unchanged under this action. That's why they are called invariant. The second is orbits. Orbits, you start from a vector and you apply all the group elements to it, so you get everything you can reach using the group. And this is called an orbit, represented by O sub v for a vector v. Okay. And it will be very important because we are working over the complex numbers, over any continuous sort of field, that we look at orbit closure. So sometimes this set of points that the group gets you to is not closed in the usual Euclidean topology, and it's very natural and very important to take closures. So that's a closure of an orbit. You just take all the limit points of this set. And you'll hear many talks during this conference where this thing will be important. Okay, so these are the three, and let me give you some examples that, again, you are familiar with of these objects. If G is Sn acting by permutations, then the invariant polynomials, you know what they are. They are the symmetric polynomials. They are called symmetric because it's a symmetric group. You don't care about the order of variables in the polynomial. When are two vectors in the same orbit? If they have the same number of components of each value, right? Then only then can the group move one to the other. And what about closures? Well, it's a finite group, so you don't have, everything is discrete.
You're very close to the edge with your chair.
Yeah, it's my, I always live on the edge. I like it like this, yeah.
Your orbit closure includes the...
We'll see. Thanks. It's always good to have friends. Serious. Second example, so we saw this conjugation example. Let's see what are these objects here. Turns out that the invariants are all, or everything generated by the traces of a power of this matrix. You don't, again, you don't see it, don't matter. It just will ring some things from maybe college algebra with you.
Same as eigenvalues.
What?
Is that the same as eigenvalues?
No, well, yeah. So orbits actually are Jordan normal forms. That's what they are invariants. They are not polynomial invariants, but they are invariants. And orbit closures here differ from orbits. I mean that we don't have to go into this, but it depends on whether the matrix is diagonalizable or not. But if you want to test whether two orbit closures intersect or not, what you have to test is whether they have the same eigenvalues. So eigenvalues are also invariant. You are familiar with them. They are not polynomial invariants, but they are determined by these polynomials. Okay, these things you've seen. And in fact, we have all over the place examples of this. Yeah, we mentioned graph isomorphism, where the action is a symmetric group, where we see our problems actually include, maybe not explicitly, but include questions about orbits and orbit closures and the relationships. So graph isomorphism is an obvious one. Relations, questions about tensors, rank and border rank of tensors. If you look at three tensors, it's rank is not affected if you act by change of basis in any one of the 3 dimensions. So you have a natural action there. I want to say that symmetries occur in lots of questions, whether or not you explicitly acknowledge it. In PIT, it's the same. You're asking whether symbolic determinant is 0. Then you can change basis on the left, change basis on the right, or change basis of the variables. In property testing, again, it's underlying for property testing of graphs. We had symmetric group and codes. Madhu and his students and his colleagues, studied the affine group acting on codes when you do property testing and the importance of that. And you'll hear a lot in the next talk and also later how in the study of arithmetic circuits or the VP versus VNP questions in the GCT program, we want to know whether, the question really is whether permanent, the polynomial, is in the orbit closure of determinant of appropriate size, and the group action is again the same. We act linearly on the variables, right? And it moves these polynomials about, and this is a group action. But I want to stress here that it's this group action, until we keep talking about algebra, this is a notion of reduction in algebraic complexity theory, this linear change of basis in the variables. So there's a very strong connection, intuitive and high-level connection between what invariant theorists are studying and what we are studying. It somehow aligns perfectly here. Okay. So these are the reductions. And it happens to be that arithmetic complexity, the reductions are group actions or very close to group actions. Here's the object that is the first I want to say some more about. So we talked about the invariant polynomials. It's clear that invariant polynomials are closed under addition and multiplication, so they form a ring. So that's what invariant theories are trying to understand. It's denoted this way. So C of V is a ring of polynomials, and you put a little g on top. All the invariant polynomials, and a fundamental, maybe I would say the big bang of the field, even though it started earlier, is these papers of Hilbert, where the main thing he wanted to prove was that this ring, in the generality I talked about, reductive rational representations in this very general setting, is finitely generated. So you can always describe, it's infinitely many polynomials, but you can always describe them by finite set, and everything it generates in the algebraic setting. It's sort of remarkable that lots of things you know about, lots of things that were so important for mathematics, commutative algebra, and also for us, like the Nussdalen-Satz and the finite basis theorem, and also algorithms like the Grobner basis. Algorithms have, started there. It's, things that Hilbert needed to prove as maybe lemmas in order to get this invariant theory result. And they became, I would say, maybe even more important than in mathematics than this result. And what invariant, question? What invariant theories, okay, so just examples. In the case of symmetric group, then you ask what generates all symmetric polynomials. When you probably know they are generated as an algebra by, or as a ring by, the elementary symmetric polynomials. It's just a finite set. In the case of conjugation, these traces of powers are generated just by the powers up to n by the Cayley-Hamilton theorem. So you know that, and in fact it's very important that this set is small, and in fact it's bounded by, if you look at Sn or GLN, the degree of these polynomials is bounded by n. It's just finite set, small, and also low degree. happens to be, just happens to be the case. In the first is the size, well, n is the number of things you act on, and the second is the dimension of the group, so it's sort of not clear what role n plays, but a very fundamental result. So one thing they are trying to do in invariant theory, get degree bounds for the generating invariants, and Derksen proved a very important theorem, much improving on Hilbert, that you can always bound the degrees as an exponential function of n, let's say when n is the dimension of the group. We'll be mainly interested in groups like that. We'll talk about this a little later. So that's the invariant ring. And just a high-level comment is that not only are structural bounds are important to invariant theories, but also algorithmic bounds. They care about algorithms, and there are books in which algorithms or computation is in the title, and there are explicit algorithms they need to. And in fact, you want to solve systems of polynomial equations, you want to compute generators in an ideal, and so on. You need, and these are for even particular actions that you want to understand. You need algorithms, and since the middle of the 19th century, they've been developing them. Yeah.
So the Derksen's result is for any P, any G, or there exists there are P's and G's for which?
For any reductive group, any rational action, rational representation of the group is of dimension n. There is a set of generators, all of them of degree at most exponential in n, which generate the whole invariant ring. Yeah. And you cannot improve in this generality. There are some that require exponential. And the main problems, sort of computational problems, they look at computational problems and structural problems. You want to describe all invariants, so that give generators, give relations between the generators. You want to get degree bounds, as I mentioned, which is a simpler problem. And then there are all these isomorphism problems that we started talking about before. When are two things the same under the group action? This isomorphism problem. So we want to understand maybe whether two orbits intersect or two orbit closures intersect. You'll hear in Ketan's talk about natural normalization and these generators problems. He'll describe it, orbit closure containment. And for the rest of the talk, I'm going to focus on one problem with simpler than all of them. It's already extremely rich, which is this null cone problem. The null cone problem is all these problems where one of these orbits is the orbit of the point 0, of the vector 0. You notice it in all these linear actions, when you act on 0, you get 0 back. So 0 is always in an orbit by itself, and you want to know whether another orbit is similar to it. Let's say its orbit closure contains 0. That's a null cone problem, and I'll just talk about this, and you'll see how familiar it is in so many ways, how general it is. It captures so many things that we care about. So I want to start giving you examples. Questions so far? Okay, let's look at the null cone problem. So here we come to the geometric point of view. So we have this group action. It creates this set of orbits. And the geometric or analytic point of view of invariant theory is trying to understand what is the what is the space? If you contract every orbit to a point, what does it look like? You want to projectivize the space somehow. In particular, you have to understand what is like 0 for this purpose. Who looks like 0? Who touches 0 and who's sort of separate? Okay, so I want to show you that captures many natural problems. Again, we have this group action, G acts on V. We have the null cone, right? All the vectors V that the group can take close to 0. And close to 0 what's the closure? What does a closure mean? That there's a sequence of group elements that will push this vector to 0. Okay? So that's what we try to understand, this null cone, and what kind of problems does it capture. It looks very particular at this point, but you'll see in a second why not. So from an analytic point of view, in fact, optimization point of view, this question is like this. I give you a vector V. To tell you whether it's in the null cone, you ask whether it can get close to 0, so you might as well look at the norm of this vector. Can you make it as small as you want by a sequence of group elements? What's the infimum of all group elements of this norm of this vector? Does it get 0 in the limit? That's the analytic view. And there's an algebraic equivalent condition for testing whether it's in the null cone. But this is, it turns out to be in the null cone exactly, if and only if, all invariant polynomials evaluate to 0 at this point. Right? And one direction is very, very simple, just because polynomials are continuous. So. The other direction that requires Null-Challenger theorem and other stuff. So that's a very important theorem, and it's important because it provides this important connection between the algebraic and analytic sides of invariant theory, and for us, it provides a connection between the optimization problems and algebraic complexity problems, and we'll see this, like PIT problems come up. You'll see now more in Ketan's talk and in Raphael's talk how PIT enters it. So that's a really important message, that there is this connection, and this connection invariant theorists knew about, and they use it, and we also use it. So here are some examples. In fact, there are many examples, I think. I just want to show you the null cone in some situations. So what's the null cone of the group action, the symmetric group acts on by permutations? When can you get 0? Well, you can get 0 only if you are 0. You are just permuting coordinates. So null cone is by itself. And there are no closures here because it's a finite group. In the case of conjugation that we saw, we said the invariants are generated by the traces of powers of the matrix. And here it turns out, and you may or may not see it, the null cone contains all nilpotent matrices. All nilpotent matrices, they can be pushed to 0 by conjugation, and the others cannot. Another familiar object. We learn lots of these things in college algebra. We never talk about group actions. We talk about, but they arise naturally. Here's another example. If you, instead of conjugation, which is multiplied by a matrix and its inverse, you look at this left-right action, you multiply on the left by one matrix and the other by another, so you change bases independently, then here the invariants are different. They are generated by a single polynomial, just a determinant of the matrix. And here the null cone is not nilpotent matrices, but singular matrices, as it turns out. Very natural object, of course. And now we come to familiar things, like what I showed you in the beginning, matrix scaling. So here, there's a group action, which I sort of didn't mention, although it's obvious when I said you normalize rows and normalize columns by constants. It's just you pre and post multiply by diagonal matrices, like this. So that's a group action. There's a group action that this algorithm was really implementing. So it's not a basis change, just multiplication by diagonal matrices. It turns out, and very easy to see, that the invariants here are generated by these monomials, which are just matchings. Right? If you look at any particular product like this, if you pre and post multiply by the diagonal matrices of determinant 1, you are not changing any of them. Okay, so that's simple. And the null cone turns out to be exactly those matrices for which the permanent is 0. So this is a direct connection to the perfect matching problem. So perfect matching arises naturally. Here we saw it already, but it's just a null cone problem. Perfect matching is a null cone problem.
Where does the determinant 1 condition come from?
Where is which?
The determinant 1 condition.
Doesn't matter. It's a good action to look at for this purpose, but you can get it also if you don't do determinant 1. It's sort of a choice. You have a graph. It has no perfect matching if and only if the matrix is in the null cone of this action. So perfect matching is a null cone problem. Here's another, even more important null cone problem that you are very familiar with, and this should say, wow. I think you should say, wow, this is a null cone problem. So here is a null cone problem for you. If I can, no, okay. Sorry. The next slide will be more impressive, but this is very important to me, and that's how this project started, in fact. When we looked at this action, it turns out this turns out to be, in some sense, a quantum generalization of the previous problem. Doesn't matter how. Here's the very natural action. Instead of acting on matrices, you act on tuples of matrices. So you have M matrices, x1 through xm, and you act on them by pre and post multiplying them by basis change, simultaneous basis change, okay, on the left and on the right. So you see the action here, right? This tuple, you pre and post multiply each of them by a matrix A and B. And here the invariance turns out to be not so easy to find. It took a long time in this sequence of works. And they are generated by an infinite family of polynomials. These polynomials are the determinants of this sum of tensor powers, and they are parameterized by this di. So you take matrices di's of all sizes, and each of them will give you polynomials in terms of the variables xi's. And it turns out that all of these polynomials generate the invariant ring. The null cone here turns out to be very interesting and manifests itself in many areas of math and, in fact, quantum information theory. It corresponds to this non-commutative singularity problem. It relates to non-commutative identity testing and other things that I'm not going to talk about. So you don't have to understand this, but it's very rich. And the first result which started this, results that started this was this paper with Rafael Ankit and Leonid Gurvitz, and followed up by a different algorithm, Ivanius, Subramanian, and Kiao. There are deterministic polynomial time algorithms to understand or to test membership in this null cone. And this algorithm used the Dirksen bound I mentioned on with exponential. It turns out exponential degree bounds were good enough for us. It's not clear even why it's relevant, but it's very relevant to efficiency analysis. And for the subsequent result, it was using the stronger results, stronger bounds. That for this action, you can get polynomial in a degree bound. That was very important. But one point to make in this algebraic workshop is that this testing here is a very interesting subproblem of the polynomial identity testing question, which is different than the type we've been looking at for many years, like polynomial identity testing for various restricted classes of circuits. This is a very structured and different kind of PIT problems. And we know how to solve this and others efficiently in deterministic polynomial time. This is what I wanted to impress you with. Also, the linear programming problem is a null cone problem. So what is the action? And what is the action on? Here the action is of this torus, right? It's just a diagonal set of matrices, just one matrix, not two. How does what does it act on? It acts on what's the vector space? The vector space of all polynomials, but let me allow polynomials with negative exponents, Laurent polynomials. And the action is the simplest thing you can think of. It's scaling. It's just like we were scaling matrices, we are scaling variables. So when we have a matrix like this, so just a bunch of diagonal terms t1 up to tn, we just scale each variable. The xi we scale by ti. This is the action. You start with a polynomial, you get a different polynomial. So you really look at the action on the coefficients of the polynomial. That's a linear action. And now, if we take any polynomial, and its support, let's say, are just, not let's say, the support is just a set of coefficients which are non-zero, and you want to know what's the null cone of this, right? This polynomial is a vector. You want to know whether it's in the null cone or not. Well, you are really asking, this polynomial is not in the null cone, if and only if the point 0 is in the convex hull of the support of this polynomial. What's the support again? Support is a set of exponent vectors. So you have this collection of integer vectors. These are the exponents appearing in your polynomial. It's a bunch of points in space. You look at their convex hull. The convex hull is called the Newton polytope. I never knew why anybody would care to take the set of exponent vectors of a polynomial and take their convex hull. This turns out to be very important in algebraic geometry. It helps counting number of solutions to systems of polynomial equations. But never mind that. You see that this object is not in the null cone exactly if a linear programming problem or membership problem in a polytope is answered yes. So it's a very natural way in which linear programming arises from a very simple group action on polynomials. Yes?
What are the invariants here?
That's not, yeah. I'll answer you later. And it turns out that there is a non-commutative analog of this, which we will see later, and we'll see a non-commutative, so this thing that naturally arises in invariant theory is also the study of non-commutative analogs of linear programming, and they have results which we'll soon see about this, and you know, that we didn't know about, I didn't know about, and it's very useful, very powerful. Yes?
So do polynomials have real coefficients?
Yes.
Okay, not complex.
Yeah, it can be complex, yeah. But it turns out it doesn't matter. It doesn't matter at this point, yeah. But at the end, what you will really look at is polynomials with non-negative real coefficients. That's what the actual polynomial you care about will have.
And is there a finite field analog of this kind of a thing?
For many of the, first of all the questions are interesting over finite, positive characteristic, finite fields. We know much less about them, about many of them, and yeah, so I restricted myself to this because that's the richer theory. Beautiful questions there. So here's the complexity theory view of what I want to tell you about this null cone problem. Where does it lie? What's the complexity in general? I've given you a bunch of examples, but where does it lie? So it turns out that morally, it's in NP intersect co-NP. And in fact, we like to make this morally into something more concrete.
What was GIT?
Yeah, geometric invariant theory. You don't remember all the acronyms from the previous slides? I don't know.
I didn't ask you what NP.
So, what do I mean by this? I mean what we usually mean in complexity theory with NP and co-NP. We have easy proofs of membership and non-membership in the null cone. The two major results are the Hilbert-Mumford criterion, which tells you how to certify membership, and there's the Kemp-Ness theorem, which tells you how to certify non-membership, and I want to tell you about both. Okay, so we have sort of easy proofs, but they are not quite polynomial time in our language, and sometimes you can make them. Yeah, and I just mentioned that, of course, there are lots of other things where morally we have this kind of characterizations of Standardsatz, positive Standardsatz, and we are trying to make them, you know, into NP and co-NP and actually P statements. So I'll do, okay, so I'll sort of run through one. I'll give a couple of examples and then talk more about the second. What's the Hilbert-Mumford criterion? How do you certify that an element is in the null cone when you want to find a sequence of elements that drive this vector v to 0? Okay, it would be nice if you could restrict your space of sequences, and you can. What they tell you is that you can restrict yourself to a compact description because you can restrict yourself to a sequence of elements that are just parameterized by a single parameter, what's called a one-parameter subgroup of whatever group you are working with. This is no loss of generality. V is in the null cone if there's a single parameter subgroup, so just mapping from the complex numbers to your group. And those elements there are driving it to 0. You don't have to follow the next slide. I just give some examples of one-parameter subgroups, but they are familiar with, you may be familiar with them. If your group is just the complex numbers under multiplication, then one parameter subgroups are just, integer powers of your parameter. If you look at the torus, you have n of these guys, then one parameter subgroups are just, you generalize the previous example. They're just diagonal elements where each one is the same t to some integer power. If you have the special torus in which determinant are 1, then you impose this condition that the sum of the AIs are 0 because you want the product to be 1. We'll see this come up in a second. And for non-abelian groups, it turns out that one parameter subgroups are really easy to understand, and that's very important, although we won't see it. They are just the previous example, only changed by a basis. Just pre and post map. That's all and the fact that you have this description is extremely important. Anyway, you don't have to remember this, it's just examples. I want to give you the example of matrix scaling in this context of this one parameter subgroup, because this really what brings up the connection between the null cone of this action and the bipartite matching. It turns out that X is in the null cone exactly, and we'll see why because of the one parameter subgroup, but that's what comes out. It's basically when this linear program is solved. This comes out of this one parameter subgroup characterization. And you know this linear program. This is a linear program that tells you that this happens exactly if there is no perfect matching. So the support is just the non-zeros of this matrix. So this comes out just from the Hilbert-Mumford criterion. And let me not do it, but this follows directly from what happens when you know that these are the one parameter subgroups, and that's what it means to drive something to 0. You get this linear inequality. Very natural. So that was the example. I want to spend more time on the Kemp-Ness condition, which is a condition showing that an element is not in the null cone. How do you certify that? Well, we said already that in order to know that something is not in the null cone, you just have to find an invariant polynomial which does not vanish on this point. That's an algebraic condition. And I would say that till this set of works, the approach to check this was, in fact, running through your invariant polynomials in some sense, the algebraic direction. But the analytic condition, which was known, but probably not applied algorithmically very much, is that it provides a much more efficient way. So let's see it. Well, we said that, or maybe let me make these definitions. We are trying to check whether V is in the null cone, so we are trying to find whether the group drives it to 0 or drives its norm to 0. So let's define this capacity after Gurwitz. He called capacity in a different context, but now we are using it for all these actions. So the capacity of V is how small can you make V by applying a group element to it. Okay? What's the minimum norm, square norm you can make it? So here is the orbit of V, and you are trying to move along the orbit and make it as close as you like to 0. And we are asking about non-membership, so we are asking about separating it from 0. And so if you can make it 0, then it's in the null cone. If it's positive, then it's not in the null cone. And it turns out you should think about, like you think in optimization, well, you are trying to minimize it. When is it minimum? You are just trying to compute gradients and see whether it's 0. And it turns out that in a very general setting, gradient has a different name. It's called the moment map. It's called the moment map. And you're trying to say whether this, let's call it a gradient, I'll define it, whether it's 0 or not. And it turns out that this is equivalent, this happens to be equivalent to the question of whether V can be scaled in the sense of what we talked about, scaling a matrix, scaling an operator, scaling a polynomial. Scaling arises naturally from this context where in the stories I told you before, it arises just of various optimization problems that people were studying. But it arises naturally here. Okay. And minimizing this, this moment map is a dual optimization problem to minimizing capacity. And there is, in fact, a duality theorem that we'll see. That's Kempf-Ness theorem. Yeah. Okay, what's the moment map? The moment map is really the gradient of this maybe non-commutative action. So what you are trying to say is, what is a gradient? You just want to understand how an infinitesimal action, infinitesimal around the identity, around not doing anything, that's the usual definition of gradient or derivative, affects the norm. So that's how the norm is affected by infinitesimal change around the identity. You should really think gradient. So it's a linear function on some space. This space is, maybe not Rn as you are familiar with, but it happens to be the Lie algebra of the group, but you don't have to care about this. Let me point out that it occurs in more general settings, but I'm not going to talk about it. But anyway, as I mentioned before, minimizing these gradients, finding out when it's zero, is a scaling problem. And I'll show you examples of this. Yeah.
So maybe you're going to get into this, but how does the group structure affect what possible directions? You think of it as a gradient, but I imagine that you have to move in directions where the determinant is 1.
No, so you don't have to worry about it, as it turns out. This Lie algebra of the group is just a linear space. It's a tangent plane to the, if you want, to the as the identity to the manifold which is your group. So it will be a linear space. It's parameterized just like Rn is parameterized by n coordinates, but in the case of GLN, for example, it will be just Mn, all n squared entries. So it will be an n squared dimensional space, turns out.
But you have to somehow understand this tangent.
You have to understand, but it will be a linear. It will be a linear functional like your favorite gradient. Yeah, it will arise from. I will not get into this.
So maybe the kind of question that I think Russell is asking is, are we going to be non-uniform with respect to the group and uniform with respect to the vector V in terms of the algorithms we're thinking?
Yeah, absolutely. So we fix the group action. We fix, I don't know, like matrix scaling is a general thing. We know what the action is, and now we give you a matrix. Can it be scaled? Or is it in the null cone? Yes. V is the input. And yeah, we'll see even more inputs. Yeah. So matrix scaling again. You ignore this. This is a calculation, how to get the moment map. Ignore it, just to show you that it's a simple calculation from the definition of derivative. And what you get out of it is this, what's this gradient? It turns out to be, it should be a vector. It's like in normal gradient. And this vector is determined by the row sums and the column sums of the input matrix. It turns out that in this description, it's row sums and column sums in L2, but it doesn't matter, you can change it. And the other thing is that you have these shifts by a constant one. They all arise naturally, and this is scaling to a uniform marginal. We are asking whether this equals 0. We are trying to make this equal 0. So we are really trying to scale the matrix. This comes out naturally from the group action. It's just an illustration. We are looking for scaling of the matrix, which gives you, uniform marginals. Here's another one, the scaling of polynomials. Actually, let me skip it. But anyway, a very simple calculation tells you that what this gradient is, and it has to do with optimizing. But okay, I want to do something else before I'm done. So lots of natural problems. This arises naturally and shows that scaling is a natural object in the context of geometric invariant theory. And again, returning to the general theorem, what they tell you is that when you want to certify the non-membership of a vector in the null cone, you have to produce another non-zero vector, right, on which the gradient vanishes. Just like we are used to in the Euclidean setting. And this theorem has two directions. The easy direction is, well, we want to, if the element we find, this non-zero vector has zero gradient, that's as close as we can get to 0. That separates, So this is sort of an instance of showing that a global minimum is a local minimum. That's the obvious, that's the easy direction. And the hard direction is, of course, the opposite. So the hard direction is showing that local minimum implies global minimum. And in the Euclidean setting, we know it. I mean, this is all about convex functions, so there has to be some convexity. When the actions are of this type, of the abelian type, then it really, follows from normal convexity. You have to do a change of variables. Let's you move to geometric programming for those who know. But anyway, this is very easy and natural. And in what these people have done and have shown that this holds in much more generality, only that the convexity that exists there is geodesic convexity. You simply have to, you're working in a different metric. But the same philosophy holds. This picture is the same. You have local minimum implies global minimum. Convexity arises naturally in this setting. So here's an example, again, matrix scaling. I'm just repeating myself, but I want to stress these two conditions. We saw using Hilbert-Mumford that testing whether X is in the null cone is the same as testing whether the support has a perfect matching. And on the other hand, testing that X is not in the null cone using the Kempness condition is just testing whether you can scale the matrix to having a uniform marginals, to doubly stochastic. They arise from this theorem. And this, this was, of course, known in optimization, but it follows out of this general theorem. And I want to, the last 5 minutes, I want to talk about this point. So we are scaling here. We talked throughout about scaling to uniform marginals. Why? In fact, in optimization, people keep scaling to, this theorem is much more general. You ask, suppose I want different marginals. What happens then? So let me tell you what happens then. And again, invariant theorists knew about this. This brings us to the last topic, which is the moment polytopes.
So just to understand, you're saying that I'm giving you a row target and a column target, and I want to get as close to this?
Yes, by fiddling with the rows, multiplying rows and columns by constants. It's a very natural question. It arrives. Yeah. So what we should be looking at, we looked at the gradient, and we asked when it was at 0. But in fact, let's look at all the gradients that arise. Right? It's at all points. So here are all the gradients. So that's called delta, the set of all gradients. So we look at all values of the moment map over all points in the space. It's a set. We can also look at all the gradients that arise in an orbit, right? We are given a point, and we look just at the orbit. And we look at all the gradients. These are two natural sets, or collections of sets. It turns out that this is a huge, result, and I think surprise, definitely to me, is that all of them, if you properly, normalize and stuff, all of these are not just sets. They are convex polytopes. They are all convex polytopes. They are called moment polytopes. And then the uniform scaling problem we saw is just a question of whether 0 is in this moment polytope. And the non-uniform scaling problem I referred to, having other marginals, just asking about another point, maybe R, whether it's in the moment polytope. That's what it comes out to be. It's a membership in a polytope. It's our favorite sort of linear programming problem. And some of this work had led to algorithms and applications. I have just an example, again, with non-uniform matrix scaling. So again, as I mentioned, you want to scale a matrix by changing its, you're multiplying rows and columns by constants to achieve a particular set of marginals here. And of course, it's a linear programming problem. But this set of marginals was known by the same theorem, was known that the set of marginals you can get to by scaling is a convex polytope. I should stress, it's not true about the set of matrices you can get by scaling. That's not a convex set. But this is a convex set. And that's just a special example. And this is a special case, this matrix scaling, in fact, is a special case of just marginal problems. You have your distribution satisfying some conditions on its marginals. A matrix is a bivariate distribution. And there are quantum analogs. Here's another example. There's a quantum analog of this. It's a quantum marginal problem. Here you are given a d-partite state, so it's a quantum state which can be represented by a d-tensor, and there's again an underlying group action there. Every player in this d players or d states can change basis for itself, and you ask what are the set of marginals. Yeah, what is the set of marginals of this objects? That I give you a tensor. It turns out that here you have to be careful. I talked about normalization. You don't talk about the states. You really want to look at their spectra. Doesn't matter why. Maybe we'll see it later. But anyway, each one of these collections of gradients turns out to be a convex polytope. So that's another example where they arise, and testing membership in this particular, quantum polytopes is something that we have algorithms for. So I need to finish. I just want to flesh out some other examples of moment polytopes. Each of them come with a famous name, Schur-Horn thing, so diagonals of matrices that are similar to a given matrix. It's not clear why it's a polytope. It's not clear why it's even convex. Set of spectra of three matrices, three Hermitian matrices, with A plus B equals C. Turns out this set of spectra is a convex polytope. And here's another, which I will not define. In all these cases, there are group actions, and what you get out is convex polytopes, and it's not clear at all why. In the other two examples, there are polytopes, and it's not clear. Well, by now it will be clear why there are group actions. Like I mentioned, the Newton polytopes, they arise from Newton. They are convex polytopes. They are moment polytopes. And let's say matrix intersection polytope is a moment polytope, even though you never thought about it like this. So there are many, many examples of these. Okay, and the last slide is just saying that we have algorithms. So the question we want to test, I give you a group action, so it defines a moment polytope, and I guess I should have called it delta, but anyway, the moment polytope. You want to know, I give you a vector, and I give you a point, and I give you some tolerance parameter. You want to know whether this point is in the convex polytope or is epsilon outside it, the usual question. And the type of algorithms we have, and we'll hear more about them, are two types, alternating minimization algorithms, which converge polynomially well in epsilon and in all other parameters. And those that apply more sophisticated techniques, I would say, that are more related to second moment methods in optimization, but in the geodesic setting, and they converge exponentially fast in epsilon. Okay, you're asking questions, but let me conclude. So there are lots of connections between invariant theory and us in questions, notions, and results. Algorithms are important. This connection I mentioned between the analytic and the algebraic sides. Invariant theory is really asymptotic in nature and quantitative in nature, very much like ours. And it has and probably requires much more, I think, complexity theory in terms of reductions and completeness and stuff. And on the other hand, symmetry occurs in lots of our problems, even if we don't acknowledge it. There are consequences. There are these algorithms that can do things that we didn't know how to do. There are some problems that are non-convex that we can solve efficiently. There are certain families of quadratic equations that we can solve this way, or linear programs of exponential size. I mean, there are techniques there that may be useful in optimizations. And there are lots of applications in other areas that I will not talk about. And just in terms of open problems, the whole project really was about doing PIT in polynomial time. So we'd like to do this. Anyway, so these are related. And talk about this, let me just mention that there are lots more available in tutorials, much longer, and write-ups and videos and so on. And that's just an advertisement to my book, which talks about other connections of our field with mathematics. Thank you.
Time for a couple of questions.
Yeah.
So you said that whatever permanent is zero or not is a null count problem. And you said that you can certify if it's zero and you can certify it if it's not. So how doesn't it put permanent equal to zero to the question of NP?
Because this is just a decision problem. We knew all along, long ago, that testing whether permanent is positive or zero is just a perfect metric.
Non-negative matrices are non-negative.
Non-negative matrices.
Yes.
Yeah, so essentially, in your result, you need to put absolute values to do the thing.
That's right.
This was
That's right. Sorry, you asked about the non-negativity.
No, I'm asking about testing whatever permanent is.
So I'll connect the two things. It was always known that if I give you a non-negative matrix, you can test whether its permanent is zero or positive. This is just a perfect matching problem. Of course, as Leonid points out, I mean, if the matrix has negative values, then it shall be hard or NP hard. Yeah, but that's not what we are talking about. In fact, as you noticed maybe, the natural question was whether you can scale it in L2. So in L2, you just care about the absolute values, and it's automatically positive. Yeah.
So the moment polytope that you...
That's okay, yeah.
So when you say you have algorithms for testing the moment polytope, how is the polytope itself described?
Just the group action is, the fact that you have the group action, it defines a polytope. I want to stress, that's a very good question, because I want to stress, I mean, until finding out about moment polytopes, I thought that always a polytope, is described either by its facets or by its vertices. It turns out that here it's described in a totally implicit way, and often it's very hard to find either the facets or the vertices. They are not known. But even if they are not, you can test, well, in some cases, you can test membership in them. Yeah.
So the analysis of a matrix scaling algorithm based on invariant theory, is it written up in one of the references?
Yeah. It's written up. So it's written up in many of these papers, but even the one that we had with Lineal Samorodnitsky, it's just written in terms of an invariant, which is a permanent. The permanent turns out to be an invariant polynomial, and that's how it's analyzed. We didn't think of it as an invariant polynomial, but the subsequent papers elucidate this point of view. Yes.
What about complexity situation when you don't close? So let's say you have a matrix, we can do it, you check whether it's exactly scalable. Yeah. Or operator, is it exactly scalable? Yeah. Actually for polynomial, I know how to do it, but I need to put some constraint like hyperbolicity.
Yes, absolutely. It's a really good question. It turns out that there's much more structure when you look at orbit closures than when you look at orbits. But the question of orbits is very interesting for lots of different reasons, and yeah, I think that it's just much less developed and we know less about it. Yeah.
So I think let's go for the break.